Hey everyone, this is 14.4 normal distributions. What I have here is a drawing of a general normal curve, which people often call the bell curve. And essentially what's going on here is often when you take a very large set of data, the data tends to fit what we call the normal curve. For example, let's say I went to Yavapai and I tried to measure the heights of every student at Yavapai. Well, probably the average might be something around, I don't know, 5, 6, let's say. And that's probably where most of our values are going to be. There's probably going to be few people up here on the very tall range and few people down here on the very short range. Most people are going to hover around that 5, 6, 5, 7 range. So the heights here are representing the frequencies, and down here you're just essentially having your individual data values. So like 5, 6 might be the mean right here, and it'll have the largest frequency. Um, in order to have, technically, to have a normal curve, you have to meet these two criteria. Your mean, median, and mode have to be the same value, and they have to be right here in the middle with the highest frequency. And also it has to be symmetric. Essentially that just means that picture a mirror down here right in the middle. This side is an exact mirror image of this side. What we're going to be talking about a lot is what percent of values lie within certain ranges under the normal curve. So we're treating everything under the curve like everything that we're measuring. So that means 100% of the data will be underneath the curve. That also means that since this divides it right down the middle, where is it? There we go. 50% of the data will lie on the right-hand side, and 50% of the data will lie on the left-hand side. And I said 1 also because often we'll just talk about decimals rather than percent. So like 0.5 data over here, 0.5 over there. And the last thing is, this is just a kind of a technicality, new notation. Often we'll be talking about what we call population rather than a sample. In the previous sections when we're calculating like the mean and standard deviation, it's technically the sample mean and the sample standard deviation, which just means that we're taking a sample of, I don't know, let's say we're measuring, women's heart rates or something like that. Well, we're not going to measure every single woman's heart rate in the world. We're going to take a sample, hopefully a good one, and then calculate the mean or standard deviation from that. For these problems, often they assume we have a population, and so all that means is we're going to use different symbols. So this symbol here looks like a weird cursive M. It's technically the Greek letter mu, and it's just going to stand for the population mean. So just think of it as the mean. Similarly, this is the Greek letter, it's a lowercase sigma, and this is the population standard deviation. So again, nothing new here. This is just mean and standard deviation now, and these are the notation that you'll see for this section. Okay, so we're not really going to be interested in looking at a set of data and determining whether it's normal or not. Often we're going to be given a set of data and we're going to be told that it's normal, and then we're going to use that fact to infer other things about it. So the very first thing we're going to learn is called the 68, 95, 99.7 rule. It's kind of a mouthful. Often it's also called the empirical rule. I just call it this because this gives you the numbers that you need in it. So the way this works is, let's say you have a normal distribution. Your mean is right in the middle. If you go out one standard deviation to the right and one standard deviation to the left, right? So this is within one standard deviation of the mean. This rule says that 68% of your data will lie within one standard deviation of the mean, so one above and one below. Right, and that kind of makes sense because, like we said, most of your values are going to be in the middle. The majority of your values are going to hover around the middle. And this just puts a number on it. Not only the majority, pretty much almost exactly 68% of the data will lie within one standard deviation. So that's the 68 part of the rule. The 95 part says if you're within 2 standard deviations of the mean. So if you go 2 standard deviations above, 2 below, you're in this big range here, 95% of the data should lie in this range. That leaves only 5% split up among these two tails over here. And again, that makes sense because a lot of your data should be hovering around the middle. You should have very little on the outside. So remember, it's a 68, 95. 68 is for 1 standard deviation, 95 is for 2 standard deviations, and you can probably imagine what the last part of the rule is. The 99.7 rule says if you go 3 standard deviations above and 3 standard deviations below, this is essentially all of your data, 99.7. That means there's only 0.3% split into these two tiny little tails, right? Because if you go back to our example of the heights of students that you have it by, for example. There's probably going to be few people way up here in the, 8-foot range or something like that, and few people down here in the 3 to 4 foot range or whatever. So that's how the rule works. It's a 68, 95, 99.7 rule, and it says 68% of the data lies within one standard deviation, so one above and one below. 95% of the data lies within 2 standard deviations, and 99.7% of the data lies within 3 standard deviations. Let me show you how we can use this. So on page 748, we're going to try number 1 here. In the italics it says, assume that the distribution has a mean of 10 and a standard deviation of 2. So I jotted that down on the side just to remind us. And we're going to use this rule to find the percentage of values in the distribution that we describe. So on number 1 here, they're saying what percent of values lie between 10 and 12. So I recommend you do this every time. You draw a little bell curve, you label your mean right in the middle, so the mean is 10, and then you find the region that they're talking about. They're talking about the percent of values between 10 and 12. So here's 10, there's 12, right? So what percent of values lie in this range? Well, we're going to have to use this rule, which means we're going to have to look at this range in terms of how many standard deviations is that. Well, notice from 10 to 12, this is 1 standard deviation, right? 1 sigma, because over here, remember, sigma is 2. So 10 to 12 is a distance of 2, that is 1 standard deviation. So we have something that we know about 1 standard deviation, right? That's the 68 part of the 68, 95, 99.7 rule. It says that if you're 1 standard deviation above and below, 68% of the data lie in there. Here's the catch though, we only have 1 standard deviation above. Technically, that rule, oops, where is it? Here we go. Whatever, there it is. This would be 8, right? Because that's 1 standard deviation below. So 8 to 10 is 2, 10 to 12 is 2. So from 8 to 12, that is your range for 1 standard deviation above and below. The rule says that 68% of the data lies in that range. Well, we only have half of that, right? Because we don't have 8 to 12, we have 10 to 12. So this whole range would be 68% of the data according to our rule, and we only have half of that. And since this is nice and symmetric, we know we literally have half of that. So half of 68, I will do that for you. Half of 68 equals 34. And that is our answer, right? Because since 10 to 12 is 1 standard deviation, and we only have half of our 1 above and 1 below, it's going to be half of 68, which is 34%. So this is one way we could use this rule. We have a range. We know that that's within a standard deviation or so. We can use that rule, do a little bit of basic math to kind of split it up or add or whatever we have to do. In this case, we get 34%. Same type of problem here. We're going to do number 3 on page 748. Same mean and standard deviation. This time they want to know what percent of values lie above 14. This one's a little bit trickier, but we're essentially going to use the same idea. The first thing you should always do, though, is figure out what is the distance between 10 and 14, right? What is the distance between the middle, your mean, and 14? Because remember, our rule always depends on how many standard deviations from the mean. Well, this distance is 4, which is 2 standard deviations, right? Because the standard deviation is 2, so 2 2's is 4, basically. So that means we should be thinking about the 95 part of our rule. So, just like last time though, we know that 2 above and 2 below would be 95%. So what's 2 below? That would be 10 minus 4, that would be about 6, right? Not about 6, that would be 6. There we go. So we know that 95% of our data values lie within this range, okay, according to that rule. So from 6 to 14, 95%. Don't forget though, we're after the percent of values above 14, right? So how can we figure that out? Well, if I know that 95% are in the middle, that means there's only 5% left, and it's split amongst these tails, 5% here and here. So if you, again, it should be symmetric, so this should be exactly half of 5%, and this should be half of 5%. So this piece here is 1/2 of 5%, which is 2.5%. And there you go. Right, so even though that 14, that value above it, doesn't directly have anything to do with the rule, we still start with the rule and we say, okay, well, we're 2 above, That means we're going to focus on the 95 rule. Oops, we're going to focus on the 95 rule. We're 2 above, so we're going to focus on the 95 rule. 2 above and 2 below we know would be 95%, so that leaves just 2.5% on each tail. And so over here, this is one of those tails, that's going to be 2.5%. So that is the answer to part 3. Okay, so the problem is, what if instead of having nice, neat divisions between your data, like we were 1 standard deviation or 2, what if you're 1.5 standard deviations? Or what if you're 0.3 standard deviations or something like that? So that rule works very nice if you have nice, clean boundaries and how many standard deviations, but in real life, we often want to find boundaries or percents that aren't 1, 2, or 3. So what we're going to have to do is we're going to have to standardize our data, and we're going to talk about what's called a standard normal distribution. So it's still a normal distribution, but the catch is, instead of having the raw data down here, we're going to have what are called z-scores. So standardized normal distributions, we standardize the data into z-scores, and z-scores simply represent the number of standard deviations above or below the mean. So down here, the very middle, instead of having your mean here, we're going to have z equals 0. Well, the reason that is because this is where the mean is, right? And the mean is 0 standard deviations from the mean. It is the mean. So that's why z equals 0 here in the middle. This value of 1 stands for z equals 1, and that means whatever this value is, it's 1 standard deviation above the mean. So we're kind of breaking off from the actual data set, and we're just taking each data and turning it into the z-score, which represents how far above or below. The negative values down here, like a -2, would mean this corresponds to 2 standard deviations below the mean. And often we're going to want to go back and forth between z-scores and raw scores, we call them. Those are our x's. This is a conversion formula that will take you from raw scores to z-scores. You take your raw score, you subtract off the mean, divide it by the standard deviation. That is now a z-score. So on page 748, we're going to try one of these problems. It says find the areas indicated by the given z-scores. We're going to do part A. So it just says what area or what percent of values lie between 0 and -1.46. These, by the way, this is z equals 0 and z equals -1.46. So again, I recommend you draw the picture before you kind of try to figure out how to plug it in the calculator, because that's what we're going to do. Here's your standard normal distribution. Z equals 0 is right in the middle, and -1.46 is somewhere off to the left because it's negative. And we're trying to figure out what percent of the values lie within this range right here. Okay, so again, we can't apply our rule from last time because we don't have just one standard deviation, we have 1.46 below. So instead what we're going to do is we're going to use a function on the calculator. So if you go to the calculator and you press second at the top left, and then you press vars, which is next to the clear button, above vars in a different color you should see distribution. That's what we're after. We're after this distribution. So if you hit second vars, you should get a second menu where your second option, I believe, is normal CDF. This is what we're after. And what this will do is normal CDF will calculate the percent of values under the normal curve within a range of z-scores. Well, that's great because that's exactly what we want. We want the percent of values under this curve within this range. And the way you enter values into normal CDF is you always enter left, comma, right value. So for our problem, all we're going to enter is, we're going to go to our normal CDF, and then we're going to enter our left bound, which is -1.46. Going to enter a comma. The comma, by the way, is above the 7 key, I believe. And then our right bound will be 0. And we're going to close our parentheses. Right, and if you just enter that into your calculator, you should get, let me tell you real quick, you should get about 0.428. 0.428. Right, and again, this is a decimal. Often we want our answer as a percent, so this is 42.8%. So 42.8% of our data should lie within this range from -1.46 to 0. So now, using this this normal CDF thing, we should be able to find the percent of values between any range. It doesn't have to be just 1, 2, or 3. And it's pretty easy because since they give you the z-scores, you just make sure, that's why I recommend you draw the picture so that you figure out which one's left and right. Most of the time you can figure it out anyways, but clearly your left bound is negative 1.46, your right bound is z equals 0. Plug that into normal CDF and it'll just spit out the percent. And so automatically the calculator will give us the answer. I just want to warn you, a lot of these problems on my math labs will say, use the table of z-scores to find this. So back in the dark ages, before people had calculators, they used to have giant tables that basically gave you, approximate answers, approximate areas under the curve given certain z-scores. So like you might be able to go to the z-table, find negative 1.46, and it'll give you an approximate z-score. It's kind of a pain. You have this huge table, and it has some kind of catches to it. I recommend you ignore the table, right? We have a calculator. The calculator gives us a better answer, and it gives us an answer easier. So even though it says to use the table, you should use the calculator. Also, it will give you a slightly different answer than the table, which is actually okay because my math labs is pretty good about this, and it'll take both answers. So ignore the table, use the calculator. It gives you a better, faster answer. Yeah. Alright, so same idea, same page, same problem. We're going to do part D this time. It says find the percent of values below negative 2.34. Again, this is a z-score, so on our table, z equals 0 is over here, negative 2.34 is somewhere down here, and we want to find the percent of values below that. We're still going to use normal CDF, but remember, normal CDF works on left bound, comma, right bound. So over here, we don't have a defined left bound, right? Our data just kind of goes off this way. In fact, it goes off this way to negative infinity, we're going to assume. So this bound is actually negative infinity to negative 2.34. Well, that's a problem because we don't have a negative infinity button on the calculator. But what we're going to do is we're basically going to approximate negative infinity by using a large negative number. So one that could work is negative 999. It's not even close to negative infinity, but it is a large negative number. And because this curve gets so small, it gets so close to 0 out here, it doesn't actually matter. You could use negative 99999, however many nines you want. You should still get roughly the same answer when you round. The error gets so small that it doesn't matter. So I would just use negative 999 as your left bound, and then negative 2.34 as your right. And again, all we're doing here is we're approximating this range over here. It goes from negative infinity up to negative 2.34. This is our approximation for negative infinity up to negative 2.34. And if you throw this in the calculator, you will get an answer about 0.0043, which as a percent is 0.43%. So less than 1% of the data will lie in that range. And that should make some sense because it's a pretty small range out there, right? Negative 2.34, you can see you have a pretty small tail out there. So that's it. So anytime you have to use, obviously we could do the same thing on the right hand side. If it said above 2.34, so maybe 2.34 is out here, it would be 2.34 to infinity, but instead of infinity we'll just use a positive 999. So that way we can do not just defined ranges, we can do stuff like above a certain range or below a certain range by using this, this trick to approximate infinity. Okay, so far we've been given z-scores or ranges of z-scores, and they were asking us for the percent of values under the curve. Here on same page number 30, we're going to do it backwards. This time they're saying find a z-score that has 20% of the area under the normal curve. So they're basically giving us the area under the curve and asking us for what z-score goes with it. So again, I recommend you draw a picture first. It says 20% of the area under the curve is above that score. This is important because that automatically means that our z has to be on the right hand side. Well, how do I know that? Well, if I say my z is on the left hand side and they're saying that 20% of the area is above it, well, don't forget, right down the middle here, there's automatically 50% to the right and 50% to the left. So if I put my z-score here and I say that 20% is above it, well, that can't be because if my z-score is on the left-hand side, there's at least 50% above it. All right, so I automatically know that if they say that 20% of the area is above the curve, my z has to be somewhere over here on the right, somewhere above z equals 0. So this picture gives me some z-score, which we're going to figure out what it is, with area above it that is 20%. So how are we going to figure this out? Well, we're going to go back to the calculator again. This is the same spot, so second vars will give you distribution. And right below normal CDF, you should find this other function, inverse norm. So inverse norm, this is how it works. It takes in area to the left of the z-score you're after, and it will spit out the z-score. So this is pretty specific. Make sure it's area to the left, because look at this picture here. Area to the left of the z-score we're after would be all the area down here, right? Well, that area is 80%. So if we want that z-score, we're actually going to have to plug in 80% in our inverse norm. Technically, you never plug in percents, you want to plug in a decimal. So down here, inverse norm, we're going to plug in a 0.80. Right? So again, just to refresh that, it's kind of specific. When you use the inverse norm function, you always plug in the area that's to the left of the z-score you're after. The way we drew this picture, z was right here, the area to the right of it was 20%, because that's what they told us, right? Area above, let's see, where does it say above again? Is above that score. There we go. 20% of the area is above that score. So here's our z, 20% above. By default, since there's 100% underneath here, that means that there's 80% below, or 80% to the left. That's what you have to plug into our inverse norm function, the area to the left of whatever z-score you're after. So in this case, we have our 80% to the left, we plug in inverse norm of 0.80, and that should give us an answer of 0.84. Now, keep track of what you're doing. This time they gave us a percent, they wanted a z-score. So this isn't 84%, right? This is a z-score. This is z equals 0.84. What is a z-score? Well, remember, a z-score is how many standard deviations above or below the mean you are. So z equals 0.84 just means it corresponds to some raw score that is 0.84 standard deviations above the mean. So basically this problem and the last problem are just switching the things you're doing. The last problem said, given a range of z-scores, what is the percent of area below it? This one says, well, we know the percent of area above some certain z-score. What is the z-score that would correspond to that? And we got a z-score of 0.84. So very common mistakes are people kind of just get in the habit of crunching the numbers here, and they'll call this as a percent or vice versa, right? In the previous problems, they'll call it a z-score. So keep in mind what you're doing. One of them takes in z-scores, spits out area. This one takes in area and spits out z-scores. Okay, so we've talked a lot about z-scores and area, but and we've talked about what z-scores are, but we haven't really tied this back to a specific set of data. This has been kind of abstract. So remember, this formula here will convert you back and forth between z-scores and raw scores. So on the same page here, number 36, they want us to, given a mean, a standard deviation, and a raw score, remember x's, these are raw scores, that just means these are like data points, they stand for something. They want us to turn this into a z-score. Well, that's actually pretty easy because this is the formula here. They give us a raw score, x is 117, so we'll plug that in for x, minus mu here is our mean, so our mean is 100, and we divide this by sigma, which is our standard deviation, which is 15. All right, so all we're doing is just plugging these pieces into the formula. We get 17 over 15, and z-scores are often rounded to 2 decimal places, so we're going to go ahead and call this 1.13. So there you go, that's our z-score. And again, tying this all together, with this mean and standard deviation, right, in your data set you have some mean and some standard deviation. The raw score of 117 is 1.13 standard deviations above the mean. Well, you know it's going to be positive, it's going to be above, because our mean is 100 and our raw score is 117. So it better be positive because that just means it's above the mean, which it definitely is. And in fact, it's 1.13. Well, that 1, remember our standard deviation is 15. So see how 117 is see how if you take your mean and you add 1 standard deviation, you get 115, right? That's where the 1 comes from. So it's at least 1 standard deviation above the mean. And that extra 2 is about 0.13 standard deviation. It's about 0.13 of 15. Right, so I know when you go through these problems it seems pretty abstract, but this really is tied to some specific values here. We're just saying that the raw score of 117 is 1 standard deviation and some change above the mean. Right, so it's 15 above and some change, right? we can do this problem backwards. Same page, number 42. This time they're giving us a mean, a standard deviation, and a z-score, and they want us to unpack that and figure out, well, what would be the raw score that corresponds to that z-score? So we're still going to use the same formula. This time we're going to have to do a little bit of algebra, though. It's pretty simple, though. Our z-score they're giving us is 1.32. X is the raw score, so that's what we're after. Our mean is 20, and our standard deviation is 6. So again, I'm just plugging in the pieces that I have in the formula, and this time I want to solve for x. So if you want to solve this equation for x, first thing you should do is get rid of the 6. Multiply both sides by 6. Cancels out here, so we get x minus 20. Over here you get 6 times 1.32, which is 7.92. Okay. And then obviously if you want to solve for x, add 20 to both sides. And let me get a little bit of room here. And you should get x equals 27.92. Right, so for this data set with a specific mean of 20 and a standard deviation of 6, the z-score of 1.32 corresponds to the raw score of 27.92. And again, we can make sense out of this because see how our mean is 20 and the z-score they gave us was 1.32? This means that our value, our raw score, has to be at least 1 standard deviation above the mean. Well, our mean's 20, so 1 above, since our standard deviation is 6, would be 26. See how we're bigger than 26? That's how we know that our z-score is bigger than 1. So that's how we can make sense of this. And the 0.32 is just means it's a little bit more standard deviation above the 6. That's how you get that extra, what is that, 1.92 or whatever. So you should be at least be able to look at this and make sense out of it to see if your answer is reasonable, right? We know that our answer has to be above 26 because 26 is exactly 1 standard deviation above. 1.32 means it's a little bit more than 1 standard deviation. Okay, so let's do one problem where we actually tie this back to some real-world data. On page 749, number 55, it says, assume the distributions of 21-year-old women's heart rates at rest is 68 beats per minute with a standard deviation of 4 beats per minute. If 200 women are examined, how many would you expect to have a heart rate of less than 70? So there's a lot of stuff going on in this problem. I would start by drawing a normal curve because yeah, they don't say it here, but somewhere in these problems it said assume that all these distributions are normal. So we're assuming this distribution is normal. We have a mean. Also, I feel like this is poorly worded for some reason. They don't say this is the mean specifically. I think it might be a typo or something in the book actually, but 68 is our mean. We have a mean of 68 beats per minute with a standard deviation of 4 beats per minute, right? So I went ahead and put our mean right in the middle, 68. That's the mean. And I made a note that our standard deviation is 4. And they're telling us that 200 women are examined. We'll use that later. It says, how many would you expect to have a heart rate of less than 70? So that's kind of the range that they're looking for. 70 would be a little bit above 68, and they want to know how many would have a heart rate of less than that. So this is the range, this is kind of the area under the curve that we're after. So first, how do we come up with that area under the curve? We can't use our 68, 95 rule, etc. because see how the distance here is 2? And see how that's half a standard deviation? Well, we can't use our 1, 2, or 3, that 68, 95, 99.7 rule. So what we can do though is we can take this 70, turn it into a z-score, and then we can use our normal CDF, right? Because this range will be, what, negative infinity up to whatever this z-score is. So let's go ahead and jump over to our z-score formula, and we'll turn 70 into a z-score. So z will be equal to 70 minus our mean, which is 68, over our standard deviation, which is 4. Well, this will give us 2 over 4, which is 0.5. We already knew that, by the way, because I said this distance is 2, and see how 2 is half a standard deviation? Well, it's exactly what the z-score tells us. 0.5 just means half a standard deviation above. So good. So now what we can do is, if we look at the normal distribution, we're actually going to be looking at the range. Let's think the z-scores over here. So it'd be negative 999 over here, all the way up to, and this will be 0.5 as a z-score, right? Because the mean would be 0 and 70 would be 0.5. So if we go to normal CDF, we're going to plug in negative 999, comma, 0.5. And if we do this, let me do it because I actually don't have it in my notes. You should get about 0.691. 0.691. That's 69.1%. I'll go ahead and just write that for you. So 69.1% of the data will lie in this range that we're after. Now, this actually wants to know, though, not what percent. It said how many would you expect to have a heart rate of less than 70. So they, out of these 200 women that they took, they want to know how many women exactly. Well, we can do that pretty easily. We know that 69.1% of the 200 women would be expected to have a heart rate of less than 70. So the question is, what is 69.1% of 200? Well, it's pretty easy. You just take the decimal, 0.691, and you multiply it by 200. And this gives you about 138.2. And this is a word problem, so not woman. It's a word problem, so we should answer it. It's 138.2 women. Right, so you can kind of see how we would use this problem, or use these values in real-world data. Most of the problems you'll do won't have anything to do with real-world data here. They'll just be asking you, trying to make sure you understand how the 68-95 rule works, how to find percentage values under a standard normal curve, etc. But it's problems like this that kind of tie it all together, right? We have a range, we know it's normal, we got our mean, standard deviation, we want to find what percent of the data lie in that range, and then, since we have a total number of women, or total number of data values, what percent of that value, or what is the value that you get when you take that percent of your total. So in this case, 69.1% of 200 gives us 138.2 women. Alright, so that is it for Chapter 14. That's it for 14.4. Let me know if you have any questions, and keep up the good work.